Imagine a newborn baby in an intensive care unit, resting under highly specialized, intense blue lights. This is phototherapy. It is a standard clinical intervention used to cure neonatal jaundice by breaking down toxic bilirubin in the blood. But completely invisibly, those same blue lights are simultaneously destroying an essential ancient molecule in that infant's blood. They are triggering a quiet, catastrophic cellular energy failure, even as they cure the jaundice. This vulnerability isn't limited to the ICU. It extends directly into the pathology laboratory. The fluorescent lights found in any hospital lab pose the exact same physical threat to a medical diagnosis. If a blood sample is drawn and left under these standard lights, the vitamin B2 inside is photo-oxidized into a useless fragment called Riboflavin. This is the pre-analytical trap. A tube that sits on a lab bench for even a few minutes can lose its metabolic integrity. When that sample reaches the testing machinery, the mass spectrometer returns a result that looks like a state of severe cellular starvation. The light has tricked the lab into a false critical low. To understand how to protect this molecule from diagnostic failure, we must first understand why its specific molecular architecture makes it both a critical manager of human energy and exquisitely vulnerable to light. Physically, this nitrogen-dense precursor consists of 3 interconnected rings attached to a 5-carbon sugar tail. In its raw state, the vitamin is inactive. Once inside the cell, enzymes attach phosphate groups to that tail, transforming it into active coenzymes, FMN and FAD. FAD makes up roughly 80% of our internal supply. It slots perfectly into specialized protein cavities called the Rossmann fold, where it dictates how enzymes handle electrical current. Given how central this molecule is to our survival, you might assume the body hoards massive reserves. In reality, our total internal content is remarkably small. A healthy adult weighing 70 kilograms contains a total body supply of just 15 to 25 milligrams. That tiny supply isn't floating freely. Roughly 80% of it is locked inside high-demand intracellular vaults. These are located in the mitochondria of the liver, kidneys, and heart, organs that never stop working. The circulating supply in the blood is even more precarious. Riboflavin has a vascular half-life of only 1 to 2 hours before the kidneys filter it out. Humans are walking on a metabolic tightrope. Without long-term storage, these vaults completely empty in just 2 to 3 weeks if diet stops, leading to systemic cellular failure. Billions of years ago, life had to solve a lethal problem: oxygen. Oxygen is greedy and rips electrons away haphazardly. This creates destructive free radicals, acting like biological rust, tearing a cell apart from the inside. Riboflavin forms a stable semi-quinone radical, holding massive energy without breaking apart. Acting as a biological surge protector, FAD trickles this energy out as safe single electron transfers, passing it down the mitochondrial chain without leaking destructive free radicals. Humans cannot manufacture this molecule natively. We depend entirely on our diet and a specific microbiome factory inside the large bowel, where bacteria like Bacteroides fragilis synthesize riboflavin for us. This bacterial pool is our survival backup. When the body senses starvation, it frantically upregulates cellular transporters called RFVT3. Think of them as thousands of new satellite dishes pushed to the cell surface, hoping to catch a stray signal of the vitamin from the backup supply. Human bioenergetics are completely dependent on this symbiosis with gut bacteria and the unique thermodynamic properties of a single vitamin. If the diet fails and the gut bacteria cannot keep up, the architecture collapses. This begins when the whole blood concentration of FAD falls below 150 nanomoles per liter. 2 critical systems flatline. First, you lose the ability to burn fat for energy through lipid beta oxidation. Second, your shield against oxidative stress drops to 0 as the enzyme glutathione reductase fails. This causes arablavinosis, where tissues with high turnover literally dissolve. It presents as angular cheilitis, painful red fissures at the corners of the mouth, and magenta glossitis, where the tongue swells and turns a deep purple red. The most desperate symptom occurs in the eye. The cornea starts suffocating from the energy crisis. To survive, the body ruins its own vision by growing physical blood vessels across the transparent cornea just to deliver oxygen. Modern medicine can accidentally trigger this exact collapse. Older psychiatric medications, specifically tricyclic antidepressants, can cause a hidden starvation. These drugs share a physical shape with riboflavin, allowing them to structurally block the enzyme responsible for activating the vitamin. A patient could be eating a perfect diet, but the medication locks the assembly line, leaving their cells to starve. There is also a genetic extreme, Brown-Violetto-Van Laer syndrome. In this condition, the cellular gateways are permanently closed. The vitamin cannot cross the cell membrane, the nervous system starves, and the patient faces progressive respiratory paralysis. Whether the cause is a missing nutrient, a pharmaceutical block, or a genetic failure, the lack of FAD results in the structural dissolution of the human boundary. To diagnose these metabolic crises, pathologists rely on liquid chromatography tandem mass spectrometry. This is the gold standard for counting the actual molecules of FAD in the blood. But the high-tech machinery is only as good as the physical discipline at the bedside. The moment the blood leaves the patient's arm, it is vulnerable to light. To prevent light from destroying the sample, blood must be drawn into an EDTA tube and immediately wrapped in aluminum foil, or collected in a specialized amber tube. The lab must keep the sample on ice and freeze the whole blood within 30 minutes. This locks down the coenzyme matrix before it can degrade. Testing the serum is unreliable, as less than 15% of the body's flavin is outside the cells. If red cells rupture during the draw, they violently leak their internal FAD stores directly into the surrounding serum. This creates a false elevation that completely masks a true underlying deficiency. Highly advanced mass spectrometry is functionally useless if the medical team fails to respect the molecule's physical vulnerabilities at the bedside. When light exposure is suspected, pathologists use a biological workaround, the erythrocyte glutathione reductase activation coefficient, or EGRAC assay. Scientists measure the baseline speed of an enzyme inside the red blood cell. Then they offer it a massive feast of artificial FAD. If its speed spikes by 40% or more, the cells were genuinely starving. No reaction means a light-damaged tube. If a true genetic transport block is confirmed, doctors move to an extreme rescue therapy. They implement a massive regimen, flooding the bloodstream with up to 300 milligrams of riboflavin daily. This creates enough physical pressure to force the vitamin through microscopic cracks in the cell membrane, bypassing the broken transporters entirely. By utilizing passive diffusion, doctors can deliver raw architectural precursors directly to the mitochondria, halting respiratory paralysis. This specialized, light-vulnerable testing requires diagnostic stewardship. Campaigns like Choosing Wisely advise against ordering expensive whole blood assays for minor symptoms. Clinicians are encouraged to rely on their own eyes first. Look for a magenta tongue. Look for angular cheilitis or corneal blood vessels. These remain the most effective initial screening tools. We have traced a journey from a primitive molecular wire that allowed oxygen survival to a structural component that preserves our epithelial boundaries, and finally to a light-sensitive analyte that requires shielding in aluminum foil just to be measured. Despite our technological hubris, human health remains tethered to 20 tiny milligrams of this light-sensitive chemical. Without it, we are never more than a few metabolic weeks away from a complete and devastating structural collapse of our biological boundaries.